little bit of bonus material now. This is about the bootstrap, and you don't have to watch this lecture if you don't want. I think there's going to be a challenge problem about this, so it'll be helpful for that. Although I think in that problem I'm also providing you some kind of code. But enjoy, okay? The point of the bootstrap is that you can estimate your standard error without doing any math. So if you remember from the previous lectures, all of the stuff that we're working on depends on having some kind of formula for the standard error defined in terms of population quantities that we can get to. And then we have to use like a plug-in estimator most often to then estimate that asymptotic standard error and then divide by square root n or something. So if we don't have such a formula, or if you don't know how to derive such a formula, so for example, for the log risk ratio where I showed, or for the variance, right? I just told you that, let's back up to the case that you're already familiar with. You know that if we have the sampling mean, this is our estimator, and we can, from here we know that the variance of this is given by the variance of x divided by n, okay? So that's good and fine. And to go from here to there, we required some IID assumptions, okay? But what if your estimator is something a little bit more complicated? What if it's the plugin for the risk ratio, right? So for the risk ratio, the estimand, remember, is the expected value of y in population where they get the exposure relative to the expected value of y in the population where we're not getting the exposure. And so the plug-in estimator for that mathematically looks kind of complicated. So this is an expected value, but it's 1 over the number where w equals 1. And here we're summing over all the cases where w equals 1, yi, and then 1 over the count where w equals 0, equals 0. This is kind of complicated already because we have the ratio of two sample means rather than a sample mean. And then really we actually have 4 sample means because this count here, well, you can express this 1 over n, you can nw equals 0, I can say as it is equal to the sum of an indicator over all n, sum of the indicator over all n, where w equals 0. And similarly, this thing, summing over just the cases where w equals 0, I can just sum y times an indicator where w equals 0, and then I can be summing over all n. And so actually I can transform this into like 2 sample means divided by 2 sample means dividing by n everywhere. So we have kind of like this function of 4 different sample means. Each of those sample means I know by the central limit theorem has some normal distribution. So actually using something called the delta method, I can show what the asymptotic variance of that is, and I did it, and that's how I got that formula that was in the, again, under some assumptions, I could get that formula for the for that standard error in this case, but it was complicated, okay? It takes some algebra, it takes some calculus and some linear algebra actually to do that, and it's hard. Honestly, it's hard. There's high probability of making an error. So if that's not something you can find immediately in a paper or something, or ChatGPT can tell you how to do it, it's pretty annoying. So it's really nice if you don't have to do that, okay? And it turns out you often don't have to. What the price you have to pay is computation. So I'll show you that in a sec. But the upside is that I can make a confidence interval without having done any math whatsoever. What I have to do instead is use computer time to repeat something over and over again. And so let me show you how this works. So first off, let me introduce the notion of a quantile function. So when I write f z minus 1, 97.5%, this refers to the value. So so first what is this? This is the density function for a random variable z, okay? This says, what is the value, little z? The value little z, such that the probability that z is less than little z is equal to whatever this number is. So in this case, I'm asking about 97.5%. So how do you compute that? Well, you can imagine conceptually, you can kind of start with z here and then little z here, and you just start increasing it. And you can just put little z as the argument into p norm, and then keep seeing what comes out until you get 97.5% of the probability, and then you stop. You say, okay, that's my value of z. So really the fz here is like p norm evaluated at this number, and then the inverse is kind of like, okay, what number do I get out of p norm? This number is 97.5% is the number I'm getting out of p norm for the value z that I'm putting in. So this is the inverse function, if you remember that from algebra or whatnot. Regardless of the notation and things like that, you just should understand that when I say big F of z minus 1 of 97.5%, I'm just asking about this 97.5th percentile of the distribution of z. That's what this little z is, and that is what is indicated by this notation. It's the quantile. So that's why it's called the quantile function. Or percentile. Okay, so let's use that for a second. I'm going to tell you, if I know the sampling distribution of estimation errors, I can tell you a confidence interval. And this holds regardless of whether it's normal and whatnot. But in the case that it is normal, we already know this, because if I know the sampling distribution, I know the truth, then I know the sampling distribution of errors. So by sampling distribution of errors, I mean the value of, it's basically just the sampling distribution of my estimate shifted over to be kind of centered at whatever the truth is. And in this case, we already know that the way that I build well, I'll just show you here why this is the case. So let A be this left value here, which is the 2.5 percentile of this distribution of errors, and B is the 97.5 percentile of the distribution of errors. So by definition, the probability that this error is in between B and A is 95%. That's just how I constructed the values of A and B. All right. Now, this is the same as this. So if this difference is in between A and B, then I can take the negative of everything, and all I need to do is switch around. If this is negative, then I need to flip this from a greater than to a less than or equal to. And same thing over here. So I'm just taking the negative value of these, and then same here. Negative of this is just that minus that instead of the estimate minus the truth. It's now the truth minus the estimate. So I just took negative of everything. And now I am adding the estimate to both sides. So if this is true, then this is true. Okay. So if this thing is in between here and here, if this difference is between here and here, then these differences are on opposite sides of this thing. So here you can ignore, if you want, you can ignore the p of whatever, and just think of these as like constant numbers, right? So you have minus p, you have this number, you have that number, and you have this number. And if this is the case, then I can add my psi hat to both sides, right? That's all I'm doing. I'm just adding psi hat to both sides and to the middle to get this inequality. And now I just still have the probability thing around it. And this is exactly what we wanted, right? Because here, this is the left bound of my confidence interval. It's psi hat minus this thing. And then here's the right bound, psi hat minus this other thing, A. So if we know A and B, then I can build a confidence interval that works, always. The only thing I need to know is what are these A and B. And that depends on knowing these quantiles of the sampling distribution of this error, all right? And we don't know that. We don't know that. If we make assumptions like, oh, it's asymptotically normal, then We know that this will just depend on, this basically like 2 times the standard error, right? But we don't know that to begin with. And we're not gonna make those assumptions in this case. So this is my 95% confidence interval. I've just plugged in the definitions of A and B, and I know it has 95% coverage because of this here, which use no assumptions really. So it all depends on knowing these quantiles, which depends on knowing what is the sampling distribution of this error. And we don't know it. It's unobserved, right? That you can imagine this, if this is our data generating process. I'm drawing it a little bit differently here now. This is a different cartoon, older slides. This is the truth. Here I sample n to get our data set, but we would like to know what is the sampling distribution if we had sampled other data sets of this error. What we can do is we're imagining that the sampling process, right, it's like if you had a population data set, it's like picking n rows from this, right? So now we're going to say, okay, I don't have the population data set, I have our data set. What if I mimic that process? So what if I pretend like the data that I observe are the population and the estimate that I calculated is the truth? So let's just go with that for a second. So what I can do is take this population data and I sample n rows from it. And here when I say sample, I mean with replacement. So I can get the same person twice, and I can get some people no times. I can get some people 3 times. So for every row in this new data set of n observations, I just go and I pick a random row from this observation and I copy it in there. Now I repeat that, and I can estimate I can apply the estimator to this new data set, and that gives me an estimate. But now I can subtract off the truth, quote unquote truth, that I know from over here, right? And I can do it again. So I can sample another data set from our data set. Again, kind of imagining that this is the population. I sample n people with replacement, and I calculate my estimate from this data set, and I subtract off the quote unquote truth, and I keep going. And now what I've gotten is a sampling distribution of my estimate from what is called the bootstrap data sets, and the sampling distribution of that estimate minus the truth, quote unquote truth, which is really the estimate in my original data set. So these are called, like I said, bootstrap samples or bootstrap data sets. And now what we're going to do is take the quantiles of this distribution that we generated. So we're going to find, we can, and so we have this distribution, like let's say we've done this 10,000 times, right? So we're just going to we're going to rank the errors that we got, right? Because it's relative to this truth. We're going to rank all the errors we got, the 10,000 of them. And we're going to take the lowest 5%, and we're going to take the highest, lowest 2.5% and the highest 2.5%. And I'm going to say, what is the value of the error at those 2 endpoints? And those are the quantiles. And let's go back to originally, okay, we know we have a 95% confidence interval if we have the quantiles of the true error distribution, but we don't have that. So what we're going to do is we're going to replace the quantiles of the true error distribution with the quantiles of the bootstrap error distribution and call that our confidence interval. So let's play around with it. So this is the same data set we had here. And we want to do a bootstrap confidence interval. So let's say for just abbreviate that. And let's do this too. Okay, so this is our estimate. And now what we have to do is, if we're going to generate a bootstrap sample, take data, and we have to do slice sample n equals n row data, replace equals true. So this is my bootstrap sample. So my original data set looks like this. And then my bootstrap sample is going to look basically the same. It's just going to be different rows sampled from that. So it looks pretty similar. We have all the same variables. It's just that what row is different. So here, like rows, it's kind of hard to see. Maybe we can just look at like the first. Let's just look at the values of z. Z. So let's look at the first 10 values of z in the original data set. Is that? And then for my bootstrap data set are these values. So you see they're different, okay? But each of these values is one of the values in the original data set. And you can see some of them are repeated, right? Oh, so like this one, for example, probably corresponds to this guy. So this guy was sampled twice in the bootstrap data set. Okay, so this is in my bootstrap data. I've gotten the bootstrap sample, and now I can take the variance of z in that bootstrap sample. And so you can see in the real data set, I got 18.7, and in the bootstrap sample, I get 17.6. In the next bootstrap sample, I'll get 17.4, 18.6, 20, so on and so forth. Okay, so let's construct the sampling distribution by doing this process many times. So I'm going to get a vector of these numbers. Yeah. Okay, so yeah, that's what I wanted. So this is my different estimates of the variance across the different bootstrap samples. And now to get the sampling distribution of the errors, I need to take that minus, errors, right? Because it's relative to the value in the true data set. Is it that minus that? It's the bootstrap minus the, yeah, okay. So this is my sampling distribution of the errors, so-called errors. And then I need the certain quantiles of that. So in R, we can do that with quantile function. I think it's like, okay. So this is the 2.5 percentile. And then we can also do the 97.5 percentile. Okay. And so here we have that we need to get the estimate minus that quantile. My CI is going to be and the upper is that minus the other quantile. There we go. So this is my bootstrap confidence interval. You can ignore these numbers here. They're just coming from this. So this is the lower bound of the confidence interval. This is the upper bound of the confidence interval. This is a lot tighter than we got with the the asymptotic version, which like makes me think that we did something wrong there. So either we did something wrong there, which is totally plausible. I could have done the algebra wrong, derived that thing wrong. Or the normal, the kind of asymptotic distribution of that thing is very far from normal. So that is also a possibility, but I think unlikely. It seems that we did something really off. So let me look into that and get back to you. But so this is bootstrapping. We can do this. You can see that at no point did I actually have to give you a formula to derive the asymptotic standard error or estimate the standard error. It just estimated it directly from repeatedly sampling from the data and computing the estimate again. So this can be kind of computationally intensive if whatever estimator you're using is something that requires a lot of computation, because you have to repeat it 1,000 times, 10,000 times, whatever, in order to get good bootstrap confidence intervals. The other thing is that this will, the numbers that you get will be different. So here I can do this again. And you can see that these numbers are not exactly the same as these numbers. So here I have 13.5 and here I have 13.47. And that's because the bootstrap samples that you get are going to be different every time you do this. So you can make this closer and closer, more consistent by making the number of bootstrap samples higher, but then it takes longer to run. So this is the trade-off, right? The kind of asymptotic expressions, if you are able to derive those, it's often nice because you can be very explicit about what matters. Like, for example, in the case of the sample mean, we could see very clearly that the only thing that mattered about the data generating distribution that influenced the variance of the sample mean estimator was the variance of the measurement, right? So it's good when you can kind of know that. It gives you intuition about what's going on in your population that is impacting how confident you can be about certain estimates. With the bootstrap, you generally don't have that kind of insight, right? So that is one advantage of the asymptotic expressions. Of course, on the other hand, this is really great because there's not a lot of assumptions that you need to make for this to work. I mean, you need to assume IID, but besides that, there's not a lot else generally that it takes in reasonable circumstances for this to work. And so you can almost always just bootstrap. And as long as you're in the IID world, then you're kind of good, right? Whereas a lot of the standard errors that you'll get from packages, standard RR packages, are based on these very strict parametric assumptions. We'll talk about that a lot more in subsequent lectures. So Bootstrap is always a good kind of sanity check. And it also, like in this case, now that I see this, I'm thinking I really must have fucked something up in my in the other case where I had the kind of like expressions for the asymptotic standard error or something, because it gives you a nice way to do a sanity check, right? That's the problem with the asymptotic formulas, is that you can always derive it wrong or misinterpret what somebody was saying in their paper. And Bootstrap is pretty kind of like brute force simple. Even this, I'm just showing you kind of long form what this looks like, but you can actually do this in R. And in the homework assignment, I have some starter code that shows you how to do this. There's a package called boot, and in that package, there's functions that basically like do this for you. I mean, it's easy enough to do it yourself. I just showed you. I mean, this is like 7 lines of code or something. So it's not that bad. But even this is like, something that can be automated to some extent using other people's R packages. So that's the Bootstrap in a nutshell. Hope you found that interesting, and hopefully it lets you at some point be able to estimate a standard error in a case where you don't have a formula for it. So, all right. Great. See you next time.